Hello, good afternoon, everyone. First of all, I would like to thank you for the invitation, especially Athens here, my very good friend. Now, I'm going to give a speech that will be a little bit different from the previous ones, because I see that the TRL of the solutions that you have shown here is quite high, and it's okay because all of the guys here are quite technical and quite of the industry sector. But I want to show you our approach as part of the academia and working in a lower TRL, trying to integrate artificial intelligence in the building sector. And before proceeding, I want to make an acknowledgement that me and my team are not exactly building experts, we are not civil engineers, but we look at this very interesting domain as data scientists. And that's the approach that I would like to showcase to you. First of all, the title shows digital twins as enablers of a smarter and more energy efficient building sector. I want to acknowledge, first of all, that what I will show is not exactly a digital twin, but they are enablers of digital twins. So with technologies that we have developed, in the next level, digital twin could be developed then. So, as I said, from the data science point of view, data and buildings. This figure, this very complex figure, is how me and my team, together with some other universities, including the team of Professor Rodas that spoke before, had understood this interesting world a couple of years ago. It was like 4 or 5 years ago, trying to submit scientific proposals. So, what we saw was 4 different layers, starting from the data itself in the blue color, going up to the end users, which should not be neglected, and they are the people that are going to use at the end of the day all these data streams. So, trying to make a graphic, let's say, landscape review, we saw that there are multiple and very heterogeneous sources of data, starting from more static data like BIM models, more dynamic data like dynamic BIM models like smart sensors, like different types of hardware with meters, with gateways, and all these fancy words that have come up in the last decade, like energy management system, building home energy management system. And to be honest with you, in the first slide, it was quite chaotic for me to try to understand which were the different things. So I decided to think a little bit simpler. So what we want to achieve at the end of the day, we want to take on these datasets, to pre-process them via different layers, as you can see. Some of those were presented also earlier, like creating, a knowledge base of all these things, the semantics, the ontologies of all these datasets, in order to have a common understanding. And I wanted to end up to the green boxes. So, first of all, we have services. So what we want to do, we want to do profiling of the buildings. Why? In order to understand how they typically behave. We want to do forecasting. We want to manage in an optimal way all the energy resources that they have. We want to assess how resilient they are. We want to enhance the comfort of the people that live there or that work there. And at the end of the day, we want to design these nice digital replicas, as I like more the term than twin, of these buildings, in order that all these entities at the upper level of this nice figure can use the service. So we have developed services for building owners, building managers, like ESCOs, energy suppliers, etc. Here in the blue color, you can see, the different categories. So we wanted to deal with the whole life cycle of the building. We achieved it relatively well, and buildings have 5 typical stages, from the design, construction, operation, then renovation, and at the end of the day also the demolition phase. So here I would like to show to you some of the instances that we have managed to develop in the last 3 years by combining our knowledge of buildings and the knowledge of experts in buildings together with our data science, let's say, expertise. So the first one refers to the operational phase, and this is a service for assessing which HVAC units should be replaced. So in our campus, and this is where we originally conceived the idea of this service, we have several offices with some of them have some air conditioning units, some heating ventilation units, etc. And within this project that we finally managed to get funded for, we had a certain budget in order to try to replace some of them. And then a very basic question came. So which are the units that is optimal for us to replace? And our building, unfortunately, did not have the chance to be as luxurious as the new one we saw. It did not have the air model, it did not have extensive smart metering equipment. So, okay, we started with some very old kind of BMS that we had, and we said, okay, we will have to bring it into life, we have to collect what data we have to generate the data sets that are missing from all these years that this BMS was inactive, and at the end of the day, we have to do some, sensible calculations in order to make this data-driven approach make sense. So what we did is we tried to, I have not put all the equations here because it would take several times. You can check this paper for more info. We tried to do which were exactly the rooms that had the most occupancy there, which was the perceived comfort of people in these rooms. So we calculated the PMV by the standards of ASHRAE, and then we also figured out what would be the financial, items like the net present value or the IRR if we replaced these units. And at the end of the day, we managed to compare the different, numbers, and we ended up, changing, replacing a couple of units in our lab. So that's a very easy example. Maybe the solution is not 100% scientific because it is based on datasets and our perception of datasets, but at the end of the day, this was a simple but practical approach. So we had this, trade-off. The second one refers to the optimal management of energy resources around the building. So unlike in the very past, that the building was just a passive, element of the whole energy sector that consumed energy. Now, buildings tend to have even active components on them, like, for example, photovoltaics in the rooftops, like, let's say, EV charging stations, that some of them might also be able to grid, so that they will give back to the grid energy when needed. Or even to have several flexible resources of energy, like we tend to say for the resources of energy that their consumption can be shifted. So, for example, we can choose when to heat our apartment. If we heat it 1 hour earlier or 1 hour later, this ends up in a similar comfort, but having also controlled our loads. So what we try to do is to try to control and push the flexible loads towards time slots during the day that the energy produced was greener. And by greener, this means that the whole energy mix of the country depended more on renewables. So what we tried to do was to model the profiling of flexible loads, like HVAC and heating, cooling loads, of batteries together with renewables, with photovoltaics, and of EV charging stations. And here you can see that we have provided for a certain building. We work with the Greek energy supplier here for that, a tentative time schedule for when it could be better or even optimal to turn on all these flexible devices. For this one, the interesting part is that, and this is related to the question that I made also to Dimitris, that all these households were not equipped with other smart meters needed. So we did not know what the fridge consumes, what the boiler consumes. We just had a central metering unit in the panel of the house, behind the meter. So we tried to apply, and I invite you again to have a look at our paper, machine learning energy disaggregation algorithm. It's called non-intrusive load monitoring for the ones that have read the literature. in order to manage with one single smart meter to estimate which appliances are on and off during certain hours during the day. And this refers also to the operational phase of the building. One last one is this tool that we managed to create. It's called Building Climate Resilience Assessment Tool, or for short, ResiBuild. And this tool, what it aims to do is to assess and estimate a building's ability to anticipate, prepare for, respond to, and also recover from climate events. These events may be drought, may be extreme heat, extreme cold, earthquakes, etc. So what we do is we created multi-criteria based system with dynamic weighting system in order to allow a location-specific resilience assessment. And what I mean by location-specific, I mean that we have taken and analyzed weather conditions, extreme events in different countries, in different geographic conditions, and we have managed to come up with a nice exposure analysis and make, let's say, benchmarking for this building, how resilient it is to heat waves, cold waves, heavy precipitation, storms, floods, droughts, etc. So here, in this graph, you can see the strong points of your buildings, the weak points of your buildings, and the next step that we are managing now to do is to give all this data from this building in the analysis of the tool to an LLM similar to the one that immediately shown, and try to push the LLM to provide to us the corrective actions for that, to give us the best possible renovation scenarios in order to make our building not just more self-sufficient and more energy efficient, but also more, let's say, resilient. At the end of the day, all these tools have been developed in a very low TRL, in scientific context. We are trying to even upscale to make them even more concrete and usable by end users. Here you can see two instances of two of our tools. And what we aim at the end goal is to use these tools in order to create and to feed all these nice digital twins that we saw earlier. These are results from the DigiBuild project that has just ended a couple of months ago, together with our key partners like engineering, like UCL, the team of Dimitris, FRT, EDF, and many others. So thank you very much, and again, I'm very happy to be able to present in front of all of you.